Hi there, this is the pre-class video for class 20. We are continuing along with chapter 7 on energy. I hope it's going well for you. Section 7.4 is called quantifying elastic potential energy. And it actually starts off with a force law, which is called Hooke's law. So Hooke is the name of a physicist who investigated springs. And the idea that if a spring is stretched, then it makes a pulling force. And if it's compressed, it makes a pushing force. And so that's one thing. And then the other thing is that the stretch distance turns out to be proportional to the force that you pull the spring, or that the spring pulls on you. So then there's these different experiments, same sort of thing. But basically, the first part of this section is telling you this equation 7.6. The force of the spring on the object that's attached to is negative kx. K is called the spring constant. It's measured in newtons per meter. So different springs, if you look at a bunch of springs in different boxes, each spring will have a spring constant labeled on it. And then X is how much you have stretched the spring beyond its equilibrium length. So X is in meters. And the negative sign tells you that if you stretch a spring by pulling it in the plus X direction, that means that the force is in the negative X direction. If you compress it in the negative X direction, that means the force is in the plus direction. It's a pushing force. Okay. All right, so that gives you Hooke's law, and the second part of this section is called elastic potential energy, in which at some point they talk about, again, the work done by the spring. So if you include the spring as part of your system, then you have a new form of energy called elastic potential energy, U sub S, which equals 1/2 kx squared. So x can be positive or negative, but when you square x, you get a positive number, times k is a positive number. So this US is always positive, and it's energy stored in a stretched or compressed spring. And they talk about shooting arrows. If you pull a bow backwards some distance, it acts like a Hooke's law, this x here, and you've got some potential energy which is proportional to x squared. And there are some questions on the pre-class quiz about exactly that. Section 7.5 is called friction and energy conservation. So friction is a force which does work, and if you're dragging it along, it tends to do negative work. But the way this all gets put into these equations for energy conservation is there's a new type of energy called in the system's internal energy. And I like to think of this as heat. So there is some actual heat created by friction, and that is equal to positive F sub k times d, where F sub k is the magnitude of the friction force on the object, and d is the distance the object moves across a surface. So when you drag an object across the surface, it creates some heat, and this is keeping track of that heat. So there's a lot of examples where what you do is, if you set up your work energy equation, the initial energy is on the left, so before you do the dragging or something like that, and on the right hand side is the final. So in the final, there's going to be some positive heat energy left over by the friction, and that's called delta U internal. INT stands for internal. And the last section is just a bunch of examples. It's called skills for analyzing processes using the work energy principle. So the work energy principle is pretty simple. It's just saying that, let's look at an equation here. Here's a good equation. It shows that the initial energy, which they represent that as K plus U, so kinetic plus potential, plus the work done on the system equals the final energy. So that's a little bit similar. If you think back to chapter 6, there was something about the initial momentum plus the impulse equals the final momentum. Well, it's a similar structure of equation, but now we're talking about energy here, so different units, and it's not a vector anymore, so it's easier actually. You've got initial energy plus the work equals the final energy. That is this, what is called the work energy principle. And so this section 7.6 is just a lot of examples. As usual, recommend that you work through, read the entire section. That's a little introduction to today's reading. Bye for now.